Thank you very much. Well, I was invited here. Thank you very much for this. Has been absolutely fantastic. The presentations here are astounding, really. And I was said here, well, could you say something regarding basic research and what that could mean? We're going to have a presentation that's going to be touching on that one. We want everyone was a creative developing environment, of course. And how should we create that? Well, of course, we have images of the brain, and we can go down to the network levels, electrophysiology on here, and molecules and genes. But of course, it's the babies we want in the end. How to better their environment and get them good. Well, I'm going to have 3 points. First, very quickly, check on synchronized cells and neuronal networks, how the rhythms in the brain develop. Because we all know that our 22,000 genes doesn't create something. It creates the background, and then it's the activity that creates who we are. Then I have to, with all the talk now of skin-to-skin care, which is fantastic and have everything good, also a bit of a word of caution of this safe skin-to-skin care. But I'm actually going to speak a lot of, well, focus most of the talk here shortly about newborn early warning scores. Because of course, you're born early and you want to have a good sleep and take care, but if you want to avoid the catastrophes, you want to avoid the sepsis, you want to avoid the neck and so on, can we do that by looking at the babies? We had the fantastic story here that you 2 days before anything happened, you could say that this baby worries me. That demands a lot of gut feeling and a lot of knowledge. But this is going to be, in the last part, going to be pilot data, but it's hopefully going to be encouraging a lot of you here to continue and better the environment here. Well, I just had to keep this slide also because this is adenosine receptors. You remember I asked about caffeine that we give all our babies, and the cerebellum is tons of adenosine receptors in it. So we had this, that the cerebellar dysfunction could cause, was one of the very important points to get bad. The other point here is hippocampus, very for the memory preservation, very important. Thus, because adenosine, that makes us sleepy. I don't know how many of you have coffee here today, but or after 2 o'clock now. Good. But it also blocks these receptors and takes away a lot of neuroprotection. The other center is the respiratory centers that highlights up here, where you can study where the respiration is generated. And it was fantastic you also said about sleep and the correlation to breathing, respiration. They're very closely correlated. And we study breathing a lot in mice, in isolated models, but of course it's the baby we does. We have some clinical studies that I mentioned, big part of the talk. This is a nice figure, I think, basically. It's illustrating the respiratory kernel, the pre-Bötzinger complex, with neurons intermingled, and these are basically the pacemaker center for breathing that makes the basic rhythm. Then this is modulated by environment, by adenosine, prostaglandins, oxytocin, everything. And you can study this in isolated models. What you have here is basically a slice of a brainstem that you can have in a dish. And you can even culture it. And next speaker here, David Forsberg, has defended his thesis regarding all of this. This is very nice. Because you can really look into the molecular effects and how interaction in the network is important. This is the breathing network. It's a model for, all the different, there are a lot of circadian rhythms, there are a lot of networks going on all the time in the brain, and we can modulate this one. We can analyze them in this way. This is what you saw there was calcium levels. There's a fluorophore that increases fluorescence when it has higher calcium levels. So it's an indirect way of measuring activity in cells. So what we have here is that we measure a lot of cells and we see how they are correlated. And then you can actually do a correlation gram here, where you can see how they are connected together. So you can describe the whole network, how it's built, and how it's modulated, and how to change its behavior. And this basically shows that this is a network, the kernel, that exists in the respiratory center. It's a small world, scale-free organization. If you have cells that are connected, you know, airports or subways, and in this case, actually, this is the Facebook contents of David here. They usually have one center, and then they're connected to other centers that are connected in a way. It's like you take an airport, with an airport, you can organize a network in different ways. You can organize it that you have, if you go from here to Copenhagen, to Amsterdam, and then all the way, if you're going to go maybe 15 flights to go down to Johannesburg. Or you can go straight for each one. Doesn't work. You have to have a Paris, you have to have a big centers. You can basically go anywhere in the world by just jumping 2 or 3 steps in airports. And this seems to be a general organization because it's energy efficient. So we have now this model how neurons interact. Yeah, small world, scale-free organization, and that demands long-term stability. And part of this, essentially, initially when we're born, one of the first molecules we're expressed with are gap junctions. Even when you have 8-cell stage, the cells start to connect to each other by channels between them, electrical channels. They can transfer RNA, they can transfer ions, and they can really modulate each other. So this is a very basic one. It's very important. Here, this is a cell which we have patched, and then it has transferred this yellow dye to the other ones. You can see faint ones in the neighborhood here also. This is just after 15 minutes. So the molecules and the cells are connected together, especially stem cells. But also a lot of the astrocytes, which we're going to speak about later on here, David. So gap junctions and their behavior are quite important for the network behavior. But you have to be cautious. Here's an example. We spoke about this rhythmic cells that were ongoing in a dish, and they do. But you see here, this is a network from a rat, and this is a network from a mouse. These guys are going on isolated by themselves. And a mice behaves quite nicely, but they have solved the problem in a different way, while rats have it in this way. So if you have, even on these two species, such a big differences, can you really use experimental models then? I think you can. But I mean, the thing you said about fruit flies is amazing. But as I said, I mean, even the larvae of the fruit flies, if you disturb their rhythm, they will have a bad brain development. But of course, is this relevant for infants? I think so. But I want to go back now to observational studies a bit, because I mean, you know, the sudden infant death syndrome, we had a lot of theories and models how that should be done. It was breathing dysfunction, it was we made a lot of laboratory assays, but it was actually the Mitchell who made the observational studies, that is what's having them on supine or prone position, that led to the big revolution. And here in Sweden we had some 100 to 140 babies per year that died in sudden infant death syndromes. Right now we're down to about 20, 25, something like that, 15. But I want to take the occasion when I'm here just to show you this, because this is something that nearly no one, well, few people know about it. Pierre Kuhn here, and I wrote a review some years ago regarding this, and it's actually basically a new phenomenon. Of course, skin-to-skin care, fantastic. This is a baby directly after birth. This is a new publication coming out right now in just a few weeks ago in Acta Pediatrica. But I want to underline safe skin-to-skin care. And we also mentioned here that when you go home from the neonatal care, should you still go on sleeping in the same bed, or how should you do it? The recommendations, I think, we actually should be to have it on their back, even if there are, of course, Mergam and I have some discussions regarding this. I think it's pros and cons. Anyhow, sudden unexpected postnatal collapse is what? Well, we defined it as, it's not surprising that a 32-week have problems with breathing and may collapse and so on. So we defined it basically as apparently healthy babies, defined over born after week 35, uncomplicated delivery, postnatal adaptation okay, APGAR score and blood gases good also. Healthy babies, and they collapse during the first 7 days, cyanosis, hypotonia, and require resuscitation. This baby, you see, she's sutured, and the mother is cuddling the baby. You can see the color of that. This baby survived. He was discovered directly after this, and had spent 2 weeks at the NICU and survived, and had a good outcome. And the parents wanted us to publish this one. This is from Switzerland, the case report originally, because this says a lot. Free airways is one of the take-home messages here. Important. So we have examined this one in retrospective in Stockholm. This is 2002 to 2006 at the Karolinska Hospital, and then the whole Stockholm community. So there's 360,000 or 70,000 babies nearly in here. And we compared it also, I mean, most of you here know that the GBS sepsis, group B, streptococci, sepsis, which is, of course, every pediatrician is very afraid of. That can cause a healthy baby to die within 2 hours. So there are a lot of programs to prevent it. When we looked here, we found, now it's 68, we had 75 we're up to right now, because they have made some more from 2018 studies also. We found 125 cases of SUPs. I mean, unexpected collapse in healthy babies, basically, or with what we thought was healthy babies. That's nearly twice the incidence of GBS. And if you ask most clinicians and read the textbooks and so on, no one knows about it. How many here knows have heard about sudden unexpected postnatal collapse? Can I have their hand up? Well, 1 out of 5-ish, something like that. Okay. Hope you'll have a take home from this one. Here's the incidence of GBS. This is just from one hospital. Here's the whole Stockholm community over the years. You see 2002, 2005, 2006, 2008, 3 years here and here. So it has decreased because we started having different programs here to decrease the incidence of GBS. Giving antibiotics and being extra, if they had a long delivery or the water has gone, you have a surveillance of the baby, basically. Yeah, the guidelines had likely make the incidence here decrease. And during all these years that we examined here, note now, no baby died. But these are babies born after week 35, or born after week 35 with a good postnatal adaptation. There were 1 or 2 babies that were really bad when they were born, so they were not even, no one thought they were in a healthy condition, basically. The one who dies are less than 35 weeks, preterms, early preterms in GBS, because people or children die still with this. No baby died. But here is the incidence of SUPs over the years. And if you see here, it declines, but nearly every year it's higher than GBS. The black dots are dead babies. So roughly 1 baby in Stockholm dies per year of this. So that's 4 to 5 babies a year in Sweden. This is not something that the hospitals and the clinics want to brag about. Oh, in my hospital, the healthy baby dies. So it has been pretty much underreported, I can say. Hopefully now we have made guidelines now, and they will decrease this. But as you see, the deaths haven't decreased yet. What we have noticed is it's important when you're born. The first 4 hours, a lot of the babies occur there. So it's directly after birth. Of course, you're fragile. You haven't started breathing in it well, so you have to be very careful in the beginning. Don't give the baby to the mom and then rush away to the other ones. Or you have a parent or someone to observe the baby, have focus on the baby. It's the important message here. And we had the theory also that we know that adenosine inhibits breathing, and we know that prostaglandin inhibits breathing. And we then examined prostaglandins and saw that, yes, every baby has tons of prostaglandins when they're born. Also the subs babies. It could possibly be so that these high levels make the baby less responsive to stress. So oxygen and carbon dioxide increased levels. Okay, but now to the important thing I want to say. I said we started with basic research. I want to go up in the clinic. Here, of course, you know, a baby that has an apnea, the first thing you do as a clinician, you throw yourself on the baby, you start to take a lot of blood tests, and you often start antibiotics even. Because an apnea can be an indication, an early indication for sepsis. And we've shown that it seems like at least the babies that you have made a lumbar puncture on, that there's a correlation to prostaglandins in the CSF. And this is likely due to this, because when we're, how many have had paracetamol in their lives? Or is there anyone here who has not had paracetamol? I'd ask, maybe. When we're sick, we have interleukins that goes out, attached on interleukin receptors in the blood-brain barrier, and then start a process of COX-2. You take COX-2 inhibitors to decrease fever. Then it's produced MPS1, which is a critical enzyme for producing fever. Produces prostaglandin E2 that then inhibits the respiratory centers here. That induces a respiratory depression, and you don't breathe in a proper way. You don't react to hypoxia or hypercarbia in a good way either. Thus, we can look at the babies. A baby who's sick. If you're experienced, you can see that, an older baby, it's easy to see that you're sick. It complains and has fever and so on. But we could also look at the infants. We can look at the prostaglandins, and we have the idea of looking at this in the urine in babies, because that would be a nice non-invasive feature instead of having a lumbar puncture in a baby. And to have that as a predictor for that it was coming to a bad end. But take home, I thought it was a rapid, nice, good biomarker that we could use that would better the healthcare of the babies. Unfortunately, it doesn't work in the clinic. It's a nice idea, but no. However, it actually, what it does, it's one of the important induces ABD events. That will say it's important for inducing the behavior of the babies. Apnea, bradycardia, and desaturations. And, let's see here. When you do NIDCAP, you make observations of the baby all the time, manual observations. It's something that calls pediatric early warning scores. It was published now in JAMA last year, and that showed that if you had observation of babies, you would then be able to see, you were able to decrease their serious deteriorations you're able to decrease. But this demands manual looking at notes. Because when we have a baby in the clinic, how does it look? Well, we have a journal system, we have other parameters, we have this. I mean, it's not very appetizing. It's hard to take home all of this information, basically. So, what has happened? Some of you remember Deep Blue, where Kasparov actually lost for a machine. Or he won the first 3, and then he lost 1, and then he didn't want to play after that. But that was some years ago. And right now, you might know that this AlphaGo for the Go, which is much more complicated than the other ones. And there's AlphaGo Zero also. And I don't know how many of you have a phone like this, or I would say how many of you have an iPhone or a mobile telephone. Most of us have. And of course, you know, the Google and Amazon are using this one for us. And they have their rumors haven't been that good. And right now we're coming into the age where this is, I think, is a bit scary, that insurance companies, they don't demand our genetic information, but they apparently want to have our physiological information. How much have you walked today? How much have you slept? Which might be good, because for them, they will prolong their life of their clients. But it will also make that you have to pay a bit less. But I mean, we're afraid of giving away our genetic information, but it's okay for giving away the physiological information. I think we're in a bit scary. However, I have to show you how we actually can use it to our advantage. Deep machine learning-based newborn early warning scores. A lot of things right now in the clinic, we say that saturation is going less than 90%, increased oxygen, CRP is going over, heart frequency is going over. I mean, you have different thresholds all the time. That's maybe not the smartest way to do it. It doesn't work, actually, if you look in the different studies. So it would be much better to be able to use the information and look at the correlations immediately. And we spent, I think, some 4 years to do this. It took some time to get through to get everything this to work. You speak to the clinicians in this fantastic new hospital, we have all the best equipment and everything is so nice and good. When you're in the clinic and want to do this, it's a bit harder. Take home, what we do is that adverse clinical events will change heart rate, respiration, temperature, blood pressure, etc. And that can actually, of course, be very early predictors for death. We have a sepsis failure, a neck, etc. But if you take this one, God helps with analyzing the data, have risk scores, you can actually start and give therapies before. What I'll present right now is actually very, very much pilot data. It's only 9 patients. 9 patients, but it's 178 days of data. And this is Carl Rombo, who's in the audience here. There, hi, who is a medical student, but at the same time also a chairman for the Swedish the parent organization, thank you, with a daughter born preterm also. So, we take information from the monitors and also from the Clinisoft standard that's stored, and also from look at the information in the journals. Because normally you have a lot of information, as said. It's very unappetizing. I mean, it's one sensor for the heart rate is 125 hertz, 125 information points per second. So we'll have 11 million points per day. One sensor. So this derives several hundred of millions of information points per patient. And if you have a big clinic, it's impossible to have a look at this, basically. If you use these data points and derive them over time, you can make nice Rorschach tests. I don't know what you see in this one. But this is 16,000 dimensions, which is then plotted down to 2-dimensional plot. Even the mathematicians I speak with don't really know all the way how to do this. But you can see what seems to happen is that a lot of people, when they get older, or this is 9 infants, as I said, they start to aggregate there in a cloud over there. So with maturation, you have this one, nice one. If you look here, you have CRP. That seems to be a bit more aggregated in the center. You do this one. But you don't need machine learning to have a CRP. You can look at the baby and you take a CRP, which is pretty fast, have an answer. However, what starts to get interesting is this. No, sorry. There. This is 9 babies, so this is very much pilot data. But in these 9 babies, you can see that if you look on these data points, you You see a cloud over here, and the red ones are when they have an adverse event. So they have a sepsis or they have an ABD event, and there's something is really happening. So even we only have 9 patients, 178 days of care, the pilot data indicates that we actually, by using this machine learning approach with a physiomarker, basically looking at the correlation between breathing, breathing depth, respiration, and heart rate, we can predict sepsis some 24 hours before it occurs. This is pilot data. This is 9 patients. Right now, we have finally got it to work. So we have now flooding a lot of more patients to be able to analyze, because I think this would be something incredible if you can have help from a machine giving a risk score. So, to finish off here, machines can learn very different strategies, and a human supervisor is actually needed. You have the cow problem, which basically says that as a baby, you can see a cow or a face, and you know it's a face, while Google needs 100,000 analyses to see a cow. And then all of a sudden, there comes a bird in the picture, and it doesn't recognize anymore. So human supervisors are needed. We need you, basically. We need interpretation. And there are no intelligence machines. Artificial intelligence is a bad word. It's what you tell the machine to do that works. And ending, you know, a baby can look like this. This was a science paper that was absolutely recently published. You can have sensors on the baby, which actually would make it possible to have a NIDCAP and still monitor for adverse events. So you could have the benefits of skin-to-skin care and at the same time be able to prevent these deleterious events. So I'm actually going to turn over now to David.